Hello everyone, welcome to Digital Communication Tutorials. In this video, I am going to take up the second numerical on waveform coding techniques. Please note, this is a numerical on delta modulation. Let me read out the question first. For the sinusoidal modulating signal x of t equals a naught into cos 2 pi f naught t, show that the output signal to quantization noise ratio in a delta modulated system under the assumption of no slope overload is given by SNR output equals 3 fs cube divided by 8 pi square f naught square fm, where fs equals to 1 divided by ts equals the sampling frequency and fm is the cutoff frequency of the low pass filter in the receiver. Right, let us start with the solution part here. First and foremost, we recognize that the numerical is based on delta modulation. Then we note that we are asked to find an expression for signal to quantization noise ratio. We know that the signal to quantization noise ratio of the delta modulated system is equal to signal power divided by noise power. Let me write it out. Let us denote the signal power as P and the quantization noise power as NQ. Let me call this as equation 1. Let us come back to the question and write the x of t signal here. So, we are given x of t is equal to a naught into cos of 2 pi f naught t. We are asked to find the signal to quantization noise ratio at the output, provided there is no slope overload. So, we will start with the condition for no slope overload. The condition is delta divided by Ts is greater than or equal to dx of t divided by dt magnitude max. Let us call this as equation 2. So, as per the equation 2, we are supposed to now find d by dt of x of t max. Let us start by d by dt of x of t. So, dx of t divided by dt is equal to d divided by dt of a naught into cos 2 pi f naught t. This is equal to a naught is constant, so I will take it outside the differentiation. Then I applied the differentiation to cos, which is minus of sine. So, it will be minus sine of 2 pi f naught t multiplied by the coefficient of t, which is 2 pi f naught. So, dx of t by dt now reduces to minus a naught 2 pi f naught into sine of 2 pi f naught t. Now, looking into the equation to RHS, what we require is the maximum value of magnitude of dx of t by dt. So, we note that the maximum value of dx of t by dt magnitude occurs when this term, which is sine of 2 pi f naught t, is equal to 1. Therefore, substituting sine 2 pi f naught t equals to 1 into the equation here, which let me call as equation 3, we obtain magnitude dx of t divided by dt max is equal to, since there is a magnitude involved, minus symbol is eliminated. So, it will be equal to a naught into 2 pi f naught, and sine 2 pi f naught of t is equal to 1 as per our assumption here. So, the maximum value of magnitude of dx of t by dt is equals to a naught into 2 pi f naught, which I will call it as equation 4. So, I will now substitute equation 4 back into equation 2, which is for the condition of no slope overload. delta divided by Ts is greater than or equal to the maximum value of dx of t by dt is a naught 2 pi f naught. I'll rearrange this for a naught. So, a naught is now less than or equal to delta divided by Ts into 2 pi f naught. Now, look at this equation, which let me call equation 5. We have less than or equal to symbol. The maximum value of a naught happens when the less than or equal to symbol is replaced by an equal to symbol. So, I will write that here as right. So, I will replace the less than or equal to symbol in equation 5 to obtain the maximum value of a naught. Therefore, a naught is equal to delta divided by Ts into 2 pi f naught. So, this is also equals to, by taking Ts to the numerator, we will get delta into Fs divided by 2 pi f naught. Let us call this as equation 6. Now, coming to the expression for the signal to noise ratio, we have signal to noise ratio is equals to signal power divided by quantization noise power. So, let us find P, which is the numerator of equation 1 here. Now, we note that the maximum average power of the input signal x of t is equal to the amplitude a naught divided by root 2 square. So, let me write that here. So, we say power is equal to a naught divided by root 2 whole square. So, this is equal to a naught square divided by 2. Let me call this as equation 7. But we have already found an expression for a naught, which is the RHS of equation 6. So, I'll substitute equation 6 into equation 7. So, we will get the power, which is the signal power, equal to a naught square, taking the RHS of equation 6. So, this would become delta square Fs square divided by, in the denominator we have a 2, multiplied by, coming to the denominator of equation 6, it is 2 square pi square f naught square. So, after simplifying, this reduces to delta square Fs square divided by 8 pi square f naught square. Let us call this as equation 8. So, we have now found the numerator part of SNR equation, which is for the signal power. Let us now move on to the noise power, which is here the quantization noise power. In my previous video, when I was discussing the delta modulation, I have already derived that the quantization noise power of a delta modulated system is equal to delta square divided by 3. Let me write that down first. Right. Now, we will assume that the quantization noise power is uniformly distributed over the frequency band up to the sampling frequency of Fs. Okay. Therefore, the output quantizing noise power within the bandwidth Fm of the low pass filter at the receiver can be given as it is represented as NQ and is equal to delta square divided by 3 multiplied by Fm divided by Fs. So, this is equals to delta square Fm divided by 3 Fs. Let me call this as equation 9. Right. So, now we have obtained expressions for the signal power, which is RHS of equation 8, and the quantization noise power, which is RHS of equation 9. So, let us substitute equations 8 and equation 9 back into the equation for the output signal to noise ratio. I will rewrite equation 1 here for the reference. So, SNR output is equal to signal power P divided by the quantization noise power NQ. Let us substitute the equation 8 RHS here. This is equal to delta square Fs square divided by 8 pi square F naught square. Then we have the quantization noise power, which is equation 9. I am going to write this by taking the denominator and numerator inverse. So, this will be multiplied by 3 into Fs divided by delta square Fm. So, let me simplify this. We have delta square here and delta square here. So, what remains is equal to 3 Fs cube divided by 8 pi square F naught square Fm, which is SNR output. Right. If you look at the last equation what we have derived here and come back to the numerical, the equations for SNR output are exactly one and the same. Thus, we have now proven that for a delta modulated system under the assumption of no slope overload, the SNR output given x of t is equals to a naught cos 2 pi f naught t is equal to 3 Fs cube divided by 8 pi square f naught square Fm. Right. That is the end of this video. If you like this video, kindly like and share this video and subscribe to my channel for more information on digital communication. Thank you for watching. Have a good day.